Well, you can flip that around, and this, you can look at the entropy of y given x. This is called the channel entropy. And if you like, this is the uncertainty from Alice's point of view. Alice sends out some symbol and figures Bob is going to get some output, but she's not sure what output Bob is going to get, because she knows it's going to be garbled along the way, perhaps. So this is Alice's uncertainty about what Bob receives, given what she sent. And generally, again, we want this to be small. Okay. It's called the channel entropy because the uncertainty comes from the noise in the channel. Okay. So here is another diagram in terms of the information entropy. Oops. I guess I'll draw it here, although it's coming up. You can draw the various entropies as a Venn diagram. So the points in the rectangle correspond to all the unique pieces of information that are there in the universe, say. And when Alice sends a source symbol, she's sending this much information, the information in this circle. When Bob receives a symbol on the other end, he's receiving this much, he's receiving this information. So Alice is sending this information, Bob is receiving this information, and these things don't line up necessarily. Now, it would be ideal if y contained all of x. That means Bob knows exactly everything that Alice knows afterwards. Okay, in other words, all the information gets through. In fact, it would be nice if x and y coincides, because then Bob is not getting any extra spurious information. He's just getting information from Alice. So we can actually interpret each little region here. So this piece, this crescent-shaped piece, that is what is that? Yeah, that's Alice's information that's lost in transit. Okay, and we want this to be small, preferably 0. How would you interpret this piece?
Incorrect information.
Yeah, it's not necessarily incorrect. It's just extraneous information that Bob is getting. And where is he getting it from? He's getting it from the noise in the channel. Bob is learning about what the noise in the channel is. Okay, and this is information that the noise is giving Bob, which presumably he has no use for. All right, he just he finds out about it, but he doesn't care about it. So the important thing is this middle piece. What is that middle piece? Yes, this is the information that Alice sends that actually does get through to Bob. This is called the mutual information. Do we want that to be big or small? Big. We want that to be big. This is the most important quantity. This is the most important entropic quantity of all of these. It's the mutual information. So the mutual information is the measure of how much information is actually getting through the channel from Alice to Bob. It's the information that the two distributions share in common. The two marginal distributions share in common. Or put it another way, it's the redundant information shared by x and y together. So here's the mathematical definition. I of x, I, standing for information, x semicolon y, is take the entropy of x and subtract off the entropy of x given y. So let's think of it this way. Here is x's information, you're going to subtract off the information about x that is not shared by y. That's this piece. This is what uncertainty is there about x once you know y. That's this crescent-shaped piece. That's the information about x left over after you've already know what y is. We're going to take all of h of x and subtract off that crescent piece, and that's going to give us this piece in here. That's why the Venn diagram is useful. You can take this, expand these in their mathematical formula definition, and you can derive this as an actual formula for the mutual information. Although we'll never have any need to compute this directly. We can get it through other means, like for example this. Okay. Take a look at this for a second. Notice one thing. What if x and y are independent? Yeah, then the joint probability is equal to the product. So this fraction is equal to 1 for all x and y. So what's the log of 1? 0. So we get 0 for the mutual information. In that case, the picture looks like this. The information content of x is completely disjoint from the information content of y. There's no overlap. There's no mutual information. So this means x and y independent. As a Venn diagram, we think of them as just there's no intersection. Okay. So here are some properties. The mutual information of x and y is the same as the mutual information of y and x, or a, b is the same as b. It's symmetric. Doesn't matter. The order doesn't matter. You can also write it this way, using the chain rule. I of a, b is h of a plus h of b minus the joint entropy. Okay? Or you could write it this way, the joint entropy minus the conditional entropy of a given b minus the conditional entropy of b given a. Okay? So, in terms of the Venn diagram, here's how now we can interpret all of these sections. So, the left circle is h of x. This is the information content of x. The size of this circle is h of x. The size of that circle is h of y. We said the size of the intersection, that's the mutual information. Well, the crescent on this side is h of x given y. This is the information content of x that is not given to you by y. It's what's left over after you know y. It's that crescent. And this crescent, by symmetry, is h of y given x. It's what you don't know about y, even if you know x. And then the total combined, the union of these two, the size of the union is the joint entropy. It's the total information content of x and y together. Okay. So just from this Venn diagram, you can go back and you can write down all the various chain rule things. They all follow from this. So for example, you can add up these areas like h of y given x plus the mutual information is equal to h of y. Just add up the regions. Combine the regions in various ways. The mutual information, you can add up the two circles and then subtract off the joint entropy. That was one of the rules we just saw. So you add up the two circles, you're counting the mutual information twice. So when you subtract the joint entropy, you're removing everything except one count of the mutual information. Okay, so there are lots of different ways to write these chain rules, but they all follow just from this one diagram, just by combining areas of various regions. All right, questions? All right, let's do another example. This is, it says long, but it's not really that long. Yes, question.
Is there a significance to the semicolon for the mutual information notation versus the comma everywhere else?
I have no idea.
Okay, so
It's a shrouded mystery.
Okay.
It doesn't. I don't really care.
Okay.
It's traditionally written as a semicolon, and I don't know the reason for that.
I'm good.
It has no significance that I know of. All right. So we're going to solve a channel here. So this is typical of what I'll ask you to do. Here is a channel given as an arrow diagram. It's a binary channel, yes? So binary input alphabet, binary output alphabet. And here's what happens. A 0 is always transmitted to a 0 with probability 1. So that will always get through. A 1, however, has a 50-50 chance of flipping. So it'll either get through a 1 or go to a 0 with equal probability. So, we're given this channel, and we're also given that the entropy, the source entropy, is equal to 1. That's all the information we have. From that, find h of y, h of xy, and the other entropies. Basically, find out everything about the Venn diagram you can. That's what we're after. All right. And the answers are given to you, so you can see what the answer is and compare it with how we do. All right. So from the arrow diagram, right, you should be able to write down the channel matrix. So first of all, what are its dimensions? It's 2 by 2. 2 by 2. The rows are indexed by the source symbols, and the columns are indexed by the receive symbols. Now, what does the first row look like? 1, 0. It corresponds to the first source symbol. Rows correspond to source symbols. What's the second row? 1/2. That's when Alice sends a 1. Yeah. Okay. All right. This is the probability of getting a 0 given a 0. This is the probability of 1 given a 0. 1 given a 0. This is the probability of a 0 given a 1. And this is the probability of a 1 given a 1. Here, it's the probability of a received symbol given a transmitted symbol.
Okay, so we're kind of going like in the shape of 0, 0, 0, 1, 1.
Yeah, so
I got the 0, 0,
mm-hmm.
but then 1, 0.
Yeah, so this is the one on the left is received, and this is sent.
Okay.
So this is a 0 being received, given that a 1 was sent.
Okay.
And this is a 1 being received, given that a 1 was sent.
Here we go. So is it the same for 0, 1? The 0 is a received and a 1 is being sent? Bottom left?
Bottom left, this is the probability that a 0 is received, given that a 1 was sent. And that you can always read that off from the arrows. So each of these arrows is a conditional probability.
Okay.
So each arrow gives the conditional probability that the head of the arrow is received, given that the tail of the arrow was sent. So here, these are the probabilities given that a 1 was sent. And here's the probability given that a 0 was sent. Here's the sanity check. If you're still not sure, here's the sanity check. Each row sums to 1. If Each row is a distribution. It's a problem with distribution. So if you flipped it, it would violate the sanity check because you'd have 1 plus a half is 3 halves. That's not equal to 1. So every row has to add up to 1. The columns don't have to add up to 1, but the rows add up to 1. Okay, any other questions about the channel matrix? All right. Source distribution. Well, this is kind of cheating. We know that the source is a binary distribution, and its entropy is 1. So that immediately tells you what the distribution is. Remember the binary entropy? It looks like this arch thing, and it hits 1 exactly where? 1/2, 1/2. So for the source entropy to be 1 with a binary source, it has to be the uniform distribution. So this has to be 1/2, 1/2. And this will be P of x, say, written as a row vector. And P of x written as a diagonal vector will then be 1/2, 1/2, 0, 0. Okay. All right, so we've got the channel matrix, and this tells us the input matrix, the source distribution, the source vector. So let's find, well, we want to find h of y. So let's find p of y first, the output distribution. So p of y is using the formula that's p of x as a row vector times p of y given x. So this is going to be 1/2, 1/2 times the channel matrix. That gives us a row vector. So what does it give us? Two-fingered rule. 1/2 times 1 is 1/2 plus a quarter, that's 3/4. All right? And so this has got to be 1/4 because of the sanity check. This is a probability distribution. And let's just check it. 1/2 times 0 plus 1/2 times a half. Yeah, that's a quarter. So that's P of y. So we can now do h of y. Well, 3/4 times log of 4/3 plus 1/4 times log of 4. And so I get 3/4 log of 4 minus log of 3. So 2 minus log of 3. And log of 4 is 2, so this is a quarter times 2. So that's a half. And so 3/4 times 2, 3/2 plus 1/2 is 2. Minus 3/4 log of 3. That's the exact simplified value. And if you plug that into your calculator, you will get approximately 0.81. So this is so notice there's some information loss here. Alice is sending 1 bit of information per source symbol, right? Because it's a uniform binary distribution, which is like a fair coin flip. So she is sending a single bit, exactly 1 bit per source symbol through the channel. Bob is getting about 8/10 of that bit, and he's losing the other. I'm sorry, yeah, he's getting about 8/10 and losing the other 2/10. Okay, so 2/10 of that, about 1/5 of that bit is being lost in the noise. All right, so we've got h of x is 1. So the big circle here is h of x is 1. H of y is 0.811. You see it's smaller because Bob is getting less information. But actually, Bob is actually losing a lot more. I got to think about So 0.811, this is what Bob is receiving per symbol, but some of this is getting actually from the noise.
So that's actually what Bob is receiving correctly?
No, this is what Bob is receiving, period. So I was wrong when I said before that this is what this is what Alice is getting through to Bob. It's not. This is what Bob is receiving per received symbol, and some of that's coming from the noise. And even less than 0.811 is he's getting from Alice. So to actually find out what Alice is sending Bob, we have to get the mutual information. Okay. Yeah.
You said it was really simple to find the row vector because the distribution is an arc.
Yeah, it's the only binary distribution that gives you an entropy value of 1. Because I drew that graph, it's like the arc, that's the St. Louis arch, and it hits 1 right at p equals 1/2. Otherwise, it's strictly less than 1. I wouldn't do something like that to you. I would actually give you more direct information about the source. Okay. So there's a little cheating going on. All right, so now we know h of x, it's 1, and we know h of y, it's given as this in exact form. So we want to find other stuff. We want to find the mutual information. Generally, the mutual information is what we're after. And one way of getting that is now we could say, for example, get the joint entropy. And then we could say add h of x, h of y, and subtract off the joint entropy. And that will give us the mutual information. So let's get the joint entropy directly by computing the joint probability matrix. So what can I erase here? I'll just set this equal to, this is h of y. I'll leave that down here. I'll erase everything else. Okay. So to get the joint entropy, we compute the joint probability matrix first, and then directly get it from there. So this is Px, the diagonal matrix, times P of y given the channel matrix. So this is going to be 1/2, 0, 0, 1/2. 1, 0, 1/2, 1/2. So this slide is good. This is the systematic way of doing things. If you then go back and redo our first example, you do the systematic way.
The bottom right should be a quarter, right?
No, I'm just copying this.
Never mind, my bad.
Okay. All right. So what do we get? Well, 1/2 into the first row is 1/2, 0. 1/2 into the second row is 1/4, 1/4. And what's the sanity check here? The sum of everything is equal to 1. Then for the joint matrix, adding everything adds to 1. It's for the channel matrix where you just each row sums to 1. So that's one difference between the channel matrix and the joint matrix. Each row of the channel matrix is a distribution, probability distribution, but this itself is one entire probability distribution. So all of these numbers add to 1, which they certainly do. So what's the entropy of that? The joint entropy is 1/2 log of 2 plus 1/4 log of 4 plus 1/4 log of 4. Well, this is nice. There are no logs anywhere. That's log of 2 is 1. That's 1/2. Log of 4 is 2. That's 2/4, so that's another 1/2. And that's another 1/2. So that's 3/2. 1.5. And that's what we got up there. Now, we're done. All we need now is the chain rule to get everything else. So, for example, to get the mutual information, we add h of x plus h of y and subtract off h of x given y. H of x comma y. So that's going to be 1 plus this thing, which is about 0.811. And then subtract off 3/2. So it's going to be about this minus a half. Because this plus 1 minus 3/2. So it's going to be this minus a half. So it's going to be 1.5 minus that, or 0.811 minus a half, 0.311. That's the mutual information. So actually, Alice is sending out 1 bit per symbol, but less than a third of that is actually getting through to Bob. So it's pretty bad. This is a very noisy channel. Questions? All right. Channel capacity. So let's go back. I'm going to go back for a second. I want to motivate this. So we've got this channel here, which is really noisy, and here's the channel matrix which describes the noise. Now, Alice happens to be sending a 0, 1 with equal probability. But Alice and Bob get together and said, how can we improve this? Maybe what Alice does is she sends a 0 a little bit more often than a 1, because she knows that a 0 is going to get through with certainty. Or maybe she sends a 1 more often than 0. I don't know. But maybe what she could do is she could tweak her input distribution to try and get more mutual information through the channel. So this is only the mutual information if Alice chooses a uniform source distribution. But if Alice chose another input distribution, maybe they could get more mutual information out of it. That leads us to the idea of channel capacity. So think of a channel. Oh, is it break time? It is. Wow, it's way past break time. Oh, let's see the glare on the clock. Oh. All right. Thank you. Thank you very much. Let's take 10. I'll come back to this. No, that was a flimsy excuse. I can just look at my watch and notice that it's...
So would it be anytime we can get a one-on-one more of a review? I'm good on like the first couple of chapters. Just in the probability has been a little rough for me. I know Trig's going to be pretty good for me. I know Ray's going to be pretty good for me. This in the last chapter is tripping me up.
The probability and then this one?
Yeah.
Okay.
So, I mean, this maybe something we can work out.
We could certainly do that.
Okay.
I also want to encourage people to work together.
Yep, we do.
For sure.
Do.
Okay. But yeah, we could, you and anyone else, maybe we could I don't know, what do you think, maybe run through some of the probability problems on the board and work them?
Yeah. I mean, and maybe like a day we get done a little quicker, but I want to do this first to see where I'm weak at. Do some more problems.
Yeah.
I'm going to do some more problems in the book too. So I'll get back with you probably Wednesday to really let you know where I'm at.
Okay. All right.
But yeah, these two I'm really worried about. I think I didn't have. I think I'm okay, and I think I'll be okay with the rest of it.
Which? Sorry.
I think I'll be okay with the rest of the way with like trig, wave.
Okay.
Okay. Thank you.
All right. Yeah. Sure.
everything. We go to our phase of their and I was thinking, what's the problem with the things that you can't? Well, no, yeah. What's that problem? What's the problem? Given the information you confirm, and you have to weigh the possibility of that person is given an attorney. Yeah, you're not in for it. You're right.
Goes into the night. Yeah. You gotta be done with this
Bambi. Do you like eating Bambi? I like eating Bambi too.
That's like the top. Like this was like if I go and see this work already on
Well, if you think about it, there's the circle of the event of all the information. And then there's what you're actually receiving, and over here you've got the groceries.
So we're at
TS clearance. That's what might happen.
I'm gonna make a Venn diagram.
You want this for how long?
Here, a couple years.
Sorry, point.
That's because my unit said, hey, you need this. And that was a big
You know what? I was part of an FA this month. We didn't need a top secret training. We weren't even doing the job that we were trained for.
So this is saying is that in the frequency band 2.4 to 5.5.
What does it say? Well,
You got you have a channel with
Men in Black suits.
when I send it, you can go to a different megahertz, but it still gets correct. Like the noise actually changes.
All right, shall we have cut a little short? Finish this? All right. Okay, so the capacity of the channel is as follows. It's the most mutual information you can get by choosing some source distribution. So you've got the channel matrix. If Alice chooses some optimal source distribution, so she decides to send a 0 3/5 of the time and a 1 1/5 of the time, whatever source she chooses to maximize the mutual information, that maximum mutual information is called the capacity of the channel. It's the most information you can send through a channel per source symbol possible, given the noise in the channel. So it's called the channel capacity. And so given the statistical profile of the channel, in other words, given the channel matrix, so any source symbol over here is translated, turns into the output symbols over here. And however you pick an input source distribution to maximize the mutual information, that's the capacity of the channel. So the capacity is the maximum overall source distribution, source probability distribution of the mutual information. So we actually know, for the simple channels I mentioned before, we actually have a simple formula for the capacities. For the binary symmetric channel, this is actually the only case I'll give you. For the binary symmetric channel with error probability P, the mutual information is maximized by Alice sending a uniform distribution of input bits. So this will actually maximize, you can provably show that this maximizes the mutual information. And the mutual information that you get is actually 1 minus the binary entropy of P. So let me draw that. That's a good picture. So remember, the binary entropy looks like this. Looks like the arch thing. Probably the 1/2. Well, if I take 1 minus this, so this is y equals h of p. So y equals 1 minus h of p. I just invert this. So let's interpret this. So this is now, P is the probability that a bit is flipped. Well, if that probability is 0, then the bit is never flipped, and Bob gets Alice's source bit with perfect fidelity. So in fact, the mutual information for the uniform distribution, the mutual information is 1, and the capacity is 1. So the capacity is able to transmit 1 bit of information per binary source symbol, and that's the maximum it can do. Now, as P increases, notice this goes down very quickly until P gets to be 1/2, What that means is that each bit that Alice sends is just flipped with 50-50 chance. So Bob doesn't get anything at this point. Nothing Bob gets. Bob is just going to get a uniform distribution of 1 and 0 regardless of what Alice sends. So in that case, the capacity is 0. There's nothing Alice can do to send Bob any information in the channel this way. Bob's distribution is essentially independent of Alice's. He's getting all his information from the noise at that point. So here's an interesting thing. Notice that the capacity goes up again as the bit flip probability goes up from 1/2 to 1. Why is that?
Because you can infer what the...
You cancel it out.
Yeah.
Yeah, so if the probability of the bit flipping is high, what all Bob has to do is just reinterpret what he receives as being the opposite. So if he gets a 1, he figures that Alice sends a 0. So he just goes ahead and flips the bit back. And that's equivalent to the bit being flipped with small probability. So in fact, if the bit is always flipped, then that's perfect fidelity again. Which is why we generally only consider P being in the range from 0 to 1/2. Because beyond 1/2, we know that Bob will just flip the bit back again. Okay. So, in general, for an arbitrary channel, finding the capacity is very complicated. It's not necessarily easy or even possible to find a nice closed expression for the capacity. You can approximate it numerically, but in general, that's a hard calculation to do. But in a simple case like the binary symmetric channel, we know exactly what it is. All right, so for the rest of the talk, I want to talk a little bit about coding. So there are 3 uses for coding. We want to remove inherent redundancy in the encoding of the original source. This is called noiseless coding, and it's used for compression. So when you apply, say, zip or something to a file, you'll get a smaller file generally. Zip is using a noiseless coding algorithm to compress the data, remove redundancy, to get the data into a smaller source. This assumes that there's no noise in the channel. That, in other words, you can compress it. You don't have to do any error correction. You just compress it. The other use for coding, though, is the opposite. Detect and correct errors that occur as the signal passes through a channel. This typically, you will expand the amount of data passing through because you build in some redundancy to be able to help correct errors. So we'll see an example of how that's done. Okay, and the idea is you want to be able to detect and possibly correct these errors without having Alice resend the information, if possible. So with no further information from the source. And finally, the third use of coding is for privacy or confidentiality. So this is called cryptographic coding, or secret codes. So which we won't talk about at all. All right. So let's talk about noiseless coding first. So there's an algorithm called the Huffman coding algorithm that gives a provably optimal way of compressing data from a source. So it depends on the number of symbols actually used in the source and the probability distribution on each source symbol. So it depends on both of those things. It requires that each symbol in the message be encoded with a unique sequence of bits, and it requires that the decoding of the message is unique. So given a code, you can uniquely recover the source exactly, so that there's no information loss. It's also called lossless coding. It's an example of lossless coding. So we're going to do an example of this. So suppose Alice is sending out symbols in a 4-symbol alphabet, say A, B, C, D, just for simplicity. And let's also suppose that she sends this long stream of, this long message, so long sequence of symbols from this alphabet. And suppose that A, so she sends, let's say, 1,000 characters, or maybe 2,000. 2,000 symbols. And in those 2,000 symbols, A occurs about half the time. So it's not uniform. So the frequency of A is about 1,000. There are about 1,000 A's in these 2,000 symbols. So the probability of A is, say, 1/2. And say only about 250 of them are B's. So the probability of B is 1/8. And C, there are about 500 C's, so probability of C is about 1/4. And D is, well, it's what's left over, which is 250. So probability of D is 1/8. Now these are reciprocal powers of 2, which makes this a pretty example, but in general the world is not so pretty. But how can we encode this into binary and maybe to store it on disk? Well, a naive encoding, I have 4 symbols. I could use 2 binary digits per symbol, right? So I could encode A as 00, B as 01, C as 10, D as 11. Okay? Then if I have 2,000 source symbols, how many bits is that?
4,000.
4,000 bits. Okay, so that's stored in 4,000 bits using a simple, naive way of coding this. But we can actually do better than that. And the reason why we can do better is because these symbols are not distributed uniformly. Here's what we're going to do. We're going to fix a binary encoding, but not all letters are going to have the same length. So here, all the lengths of the code words they're all of length 2. But here's what we're going to do instead. A occurs most frequently. So we're going to prefer more frequent letters get shorter codes. And then save the long codes for letters that are less frequent. So A is going to be encoded, say, as a 0. Just a single 0. All right. Well, here's the thing. If we're going to just concatenate these bits together, it's just one long stream of bits. The problem with encoding each character as a different length of bits is you need some way of telling when one encoding stops and the next symbol starts. So they have different lengths. So here's how we're going to do that. All we have to do is make sure that no code word is a prefix of any other code word. So when we get done with one code word, we know that's it. And we can start with the next one. There's no ambiguity. So such a code is called a prefix code. No code word is a prefix of any other code word. Well, if a 0 is going to be reserved for A, then the other 3 letters can't start with a 0. So they have to start with a 1. Okay. But we're not done because now, I have to add some stuff to these to differentiate them. Well, what's the next most frequent letter C. So maybe I'll do the minimum I can on C. I'll add a 0 on it. Okay. And if I do that, I've got to put something on these, otherwise they're going to be prefixes of that. And I can't put a 0 on them. I have to put a 1 on them. So put a 0 on them, they'll collide with that, or this is going to be a prefix of them. Now I just need one more bit to differentiate the B and the D. So arbitrarily, I'll make that a 0 and make that a 1. That is a prefix code. Okay. So let's actually encode something and decode it. So here's a sequence of things: A, B, C, A, C, D, B, C, A. Okay. There's a sequence that Alice wants to encode. So here's what she does. Encodes A as a 0, B as a 1, 1, 0, C as a 1, 0, A as a 0, C as a 1, 0, and so forth. You see what's going on. Okay. Now Bob gets the stream of bits on the other end, so there's no noise here. He gets the exact same stream of bits. How does he decode? He sees a 0. He knows that has to be an A. So he turns that into an A. He makes the dividing line there. And he says, okay, I start the next one out. He sees a 1. He doesn't know what it is. He sees another 1. Now he knows it's either B or D. And so the third bit says it is a B. Then he sees a 1 and then a 0, so that's what? C. It's got to be C. Then he sees another 0, that's an A. Then he sees a 1, 0, he knows that's a C, and so on. So he actually recovers this in a lossless way. Here's another way of picturing this code. You can draw this code as a binary tree. So maybe I'll write it up here. Think you start at the root, and then if you go down to the left, that corresponds to generating a 0. And if you go down to the right, that corresponds to a 1. So you go down until you get a complete code word, and then you label that leaf with the source symbol. So that codes A. Just a single 0. If you follow a 1, if you then follow a 0, that codes what? It codes C. But if you follow a 1 and then another 1, then the 0, 1, this is going to code a B, and that's the D. So here's the thing. In a prefix code, in a binary prefix code, you can always describe it as a tree where all the source symbols are just labels on leaves. And internal nodes, you have 2 directions to go. And so Bob decodes the same way Alice encodes. He starts at the top, and he reads off the bits, and that tells him how to go down through the tree until he hits a leaf, and then he spits out that source symbol, and then he goes back to the top and keeps doing it. Okay, so Bob can decode very quickly this way, just in real time. Okay, so this is very easily decodable. All right. Now, this actually, if we code this way, we're not losing any information, but this is going to be less than 4,000 bits. So let's see how many bits it takes. So A has length 1, so the number of bits is equal to 1,000 times 1 plus 250 times the length of B, that's 3. So this is the number of B's times the length of B. This is the number of A's times the length of A. plus the number of C's, which is 500, times the length of C, which is 2, plus the length of D, or the number of D's is 250 times 3. So what does this equal? I'd get 1,000 plus, that's giving me another 1,000. 750, 750, so 1,500. So 3,500. 3,500 down from 4,000. So that's a compression of about of 1/8. So we've actually managed to compress this file down by 1/8. Okay. And we haven't lost any information by doing this. So let's try another example. Let's be simpler. Let's suppose X itself is just the binary alphabet, 0 and 1. Okay. But 0 occurs most of the time. Maybe it occurs, I don't know, maybe like 3/4 of the time. And 1 only occurs 1/4 of the time. Now, but it's binary. So it doesn't look like we can compress this, right? Because, you have to encode 0 as something and you have to encode 1 as something. So encode 0 as a 0 and 1 as a 1. It doesn't look like you can compress this. But this is non-uniform. So actually we can compress it. Okay. Here's the theoretical compression. A source. So this is the theorem. This is called the noiseless coding theorem. A source X can be compressed to arbitrarily close to H of X bits per symbol with no loss of information. But no less than this. So the noiseless coding theorem says there is some way, take any number that's bigger than h of x, there is some way to compress that file down to a size which is essentially as close to h of x bits per symbol as you'd like. But you can't go less than that. It's impossible to go less than that without losing information. So h of x, we said, was the information content per symbol. Well, this gives us another nice interpretation of h of x. It's the number of bits you need to encode each symbol in some optimal compression scheme. So it really gives you the information, the inherent information content per symbol. And you can't go less than that without losing information. So how do we do this? So the entropy here is, it's less than 1. In fact, it's considerably less than 1. But this Huffman code doesn't do it for us, at least if I use one symbol. So here's the trick. Don't do a Huffman code on each symbol individually. Group the symbols together, say, in pairs. And treat each pair of symbol as a new source symbol. So 0, 0 we'll call A. 0, 1 we'll call B, 1, 0 we'll call C, and 1, 1 we'll call D. So if I chop up the string of bits into 2-bit blocks, I take each block as a new source symbol. So now I have an alphabet of size 4. And this alphabet has probabilities for each, and they're not uniform. So what's the probability of A? Yeah, so the chances you're going to get an A is 3/4 times 3/4, which is 9/16. And B is 3/16. And C is also 3/16. And D is going to be 1/16. This will actually allow us to compress it, at least somewhat. So here's how we can compress it. A is still the biggest. So we'll get A is 0. But then I have B and C. Well, okay, so one of these is going to be B, and then I'll have to relegate the other one, C and D. I'll put on the same level like that. So A goes to 0, B goes to 1, 0, C goes to 1, 1, 0, and D goes to 1, 1, 1. And now you can actually show that this compresses things better than just picking 2 bits per symbol. So actually, this we get less than 2 bits per symbol. So that's 2 bits per symbol in the 4-letter alphabet. Each of these was 2 source bits. So this is less than 2 bits per 2 bits of source. So it turns out to be less than 1 bit of source. Less than 1 bit per bit of source. So this actually compresses things. And this doesn't compress things perfectly. So what you could do instead is you can go one step beyond this. You can take blocks of 3 bits each. And now you have an 8-character alphabet, which has probability distribution of a certain size, and you can find an optimal way of compressing that. Yeah.
So I'm looking at your tree. It's by that standard, you would never get B. It's just 0.
No, it's 1, 0.
It's 1, 0.
You're saying you get 0, 1. You get B.
No, look down below.
Oh, yeah, okay. So forget this for a second. So what I'm doing is I'm taking bits, coding them into alphabet of size 4, and then recoding that back into different bits. So here's what Bob does. Bob reads this code, recovers which of the 4 symbols it is for each one, and then takes it one step further and goes back and converts these into bits using this. So it's a 2-step process for Bob.
He receives a 1, 2.
So let me show you how to actually do this in general. So here's how Huffman coding actually works. I have an alphabet, say x1 through xn, and xi has probability piece of I. Okay, so the sum of piece of I is equal to 1. So do the following until there's nothing left. Okay, or do the following until you get a complete tree. So repeat the following. Take 2 symbols with the smallest probabilities. two smallest probabilities. Let's say X and Y. Create a new symbol, which we'll call Z. And make Z a parent with X and Y as the two children. With probability, and Z has probability equal to the probability of X plus the probability of Y. So what we're going to do is we're going to sort of lump X and Y together into one symbol whose probability is the sum of the two probabilities of X and Y. We remove X and Y from the alphabet and add Z back to the alphabet. So remove X and Y from alphabet. Add Z to the alphabet. So insert Z into the alphabet. So we're removing two symbols from the alphabet and we're putting one new one back in. So the alphabet, the size of the alphabet decreases by 1 by doing this. Do this until the alphabet just has one symbol in it. That gives you the entire tree. Do until has one symbol. This is the tree. This is the what's called the Huffman coding tree. So for our example, well, now I'll just pick an arbitrary example. So let's suppose I have A occurs 0.1, that's its probability. B is 0.3, C is 0.05, D is 0.2, let's see, 3, 2, 5, E is 0.15, so that's 2, 4, 7, 8, F is 0.1, and G is 0.1. Okay, something like that. I just made that up. The numbers add up to 1, hopefully. So take out 2 with the smallest probability. What are those going to be? C and I actually have a choice for second. If you have a choice, doesn't matter which one you choose. Choose whichever is convenient. Let's take A. So C and A. Let's call this H. And what's its probability? 0.5 is 1, so this has probably 0.15. Okay. So C and A are gone, and H is now part of the alphabet. So now do the same thing again. What are the two smallest? F and G. Combine them with a parent. So F and G, and let's call their parent I. So I'm just picking new symbols. I has what probability? 0.2, because I add them. So F and G are now gone. Now I've got H and I. So what are the two smallest?
E and H.
E and H. So I combine E and H. Like that. And I'll call this J. All right, just picking new letters. Okay. And what's its probability?
0.3.
It's 0.3. Okay. 0.3. So E is now gone, and H is now gone, and I just have J. So now what are the two small ones? D and I. They both have 0.2. So I add a D here, and I'll combine them, and I'll call that K. And it's 0.2 plus 0.2 is 0.4. So now I is gone, and D is gone. What do I have left? I just have three letters. I have B, J, and K, and I combine B and J. And actually, it doesn't matter which side it's on. It's just, in terms of the optimality of the code, it doesn't matter. So what's this going to be?
0.6.
Yeah, so I'll call this L, and that's 0.6. Now I only have two left. I have L and K, so I just combine them because they're the two smallest into one root like that, and there's my tree. So if I want to redraw the tree over here, I have B, E, C, A, and here I have D, F, G. I'm just retaining the original letters and forgetting about those new symbols that were just temporary. There's a Huffman code. This Huffman code is gives you a provably optimal prefix code for this alphabet. And to get the actual theoretical best compression, which is entropy bits per symbol, you could, for example, take Huffman codes of blocks of two letters at a time or 3 letters at a time. The more letters you get, the closer you will get to the optimal compression. Okay, so it approaches h of x as a limit. All right, questions on Huffman code? So I don't really. This is noiseless coding, and this actually works pretty well. Well, the problem with this, practically speaking, is that you have to know what the frequencies are. Now, if you're compressing English text, we know pretty well what letter frequencies are. In fact, we know what digram and trigram frequencies are as well. So we can compress English text pretty well. But if it's not English text, if it's something else, like data from, some experiment, we don't know what the frequencies are necessarily. Now, what you could do is you could do one pass through all the data and count the frequencies up and get the probabilities that way. But for a large data set, that takes too long. People don't want to do that. So there are other schemes, compression schemes, that run quicker, that just do one pass through the data and compress it, that aren't quite as good as this, theoretically, but they're much faster. And so for practical purpose, those are used instead. The one that Zip uses is called the Lempel-Zip scheme, and used to be proprietary until about 10 years ago, when it's now public domain. That's all I really want to say about noiseless coding. There are other compression schemes. I want to talk a little bit before we quit about noisy coding. So noisy coding means an error-correcting code, or a code that can at least reduce the probability of error. And I'm just going to do a very simple example. Stick with the binary symmetric map. 1 minus P, 1 minus P, 1. Okay. So here's a simple thing that reduces the error. just take each bit and repeat it 3 times. So if Alice wants to send a 0 to Bob, she actually just sends 3 zeros to Bob. If Alice wants to send a 1, she sends 3 ones instead. Each individual bit is going through the channel, and it has a probability P of being flipped. Okay. What does Bob do on the other end? If Alice sends a 0, Bob might get 0, 0, 0. So here, P is say less than that. But he might, one of these, or maybe 2 of them might be flipped, right? Well, one of them might be flipped, so he might get that instead. Or he might get that. Or he might get that. Whoops. He might get that. If he gets that, what should he do?
Zero.
Yeah, I should interpret it as 0. What if he gets that? Yeah, so Bob's best bet is to actually just do what's called the majority of 3 decoding. He gets his 3 bits, he gets a 3-bit block, and he interprets the bit as being whatever is the majority of those bits. Okay. So here, he will correctly recover a 0, correctly. For here, though, he'll make a mistake. And likewise for that, and for that, and for that. So this is an error. This isn't correct. Assume Alice is sending a 0, 1 uniformly. So she's flipping a coin. She's sending it. Does this reduce Bob's error? Yeah, it does. It does. So what is Bob's error, chances of error? Let's imagine Alice is sending a 0. It's going to be the same if Alice sends a 1. So he's going to get an error if, for example, all 3 of them are 1s. What's the probability of that happening? Yeah, this is P cubed. So each one of these 1s occurs with probability P. If Alice is sending a 0, each one being flipped has probability P. So that's P cubed. And the other cases, 2 of them are flipped and 1 of them isn't. So 2 of them being flipped, that's P squared. And the other one not being flipped, that's 1 minus P. And there are 3 modes where that happens, so we multiply that by 3. And simplifying, this is going to be 3p squared minus 2p cubed. And if you graph this, so if this is equal to y, in terms of p, you get a curve that looks like that. What that means, if p is less than 1/2, say right there, this is the probability of error without the coding. This is the probability of error with the coding. So this reduces the error probability effectively. So effectively what's happening is that Alice and Bob are turning this channel from having an error probability P to having an error probability of this. So they're effectively reducing the error rate in the binary symmetric channel to something smaller. But this, of course, comes at a cost. What's the cost? Yeah, more bits. More bits overhead. Okay, so she's sending 3 bits instead of 1. So the rate of this code is 1/3. Rate is the number of source symbols divided by the number of bits. That's it. We'll call that R. Okay. And just time. Actually, I'm a little over. But let's end. I'll give you the noisy coding theorem. Let the channel, or let C be the capacity of the channel. For any R less than C. Let me say there are error correcting codes. With rate at least R. And with arbitrarily small. Arbitrarily small error probability. So the code we showed decreased the error probability. It's not very sophisticated. There are much more sophisticated codes that have a much smaller rate. And noisy coding theorem, this is due to Shannon, said that you are able to get any rate up to as close as you want to the capacity with error probability as small as you want. Now, bear in mind, if you come very close to the capacity and you want a very small error rate, you might have to pick a complicated code. But these codes do exist. And so the noisy coding theorem says that you can effectively, reliably send information at any rate below the capacity with arbitrarily small error. And routers and wireless antennas do this kind of calculation all the time. They estimate the capacity of the channel, and they choose an error-correcting code based on that to make the error probability extremely small. So they do things like this. The noisy coding theorem actually doesn't tell you how to find the code. It just tells you that it exists. It's not very constructive. There's a whole branch of algebra called coding theory. And the main goal of coding theorem is to find good error-correcting codes. Okay. So I don't have, I'm way out of time, so that we better stop there. Okay. Any questions?
I'm sure I'll have some.